We have all 80 stable elements on display here, plus bismuth, which is not stable. It has a very long half-life. But here they are, by block. I don't do the electron configuration thing. Because I'm more into the isotopes and stuff than anything. So the nuclear part of it, not the chemical part. The chemical part is a good way to divide it up, like as a ruler and stuff, which is why I use the blocks here. Okay. I need some water. Okay, so we start with hydrogen, right? Hydrogen, just in an ampule. Part of the S block, technically, but since that's the only block in the first period, it's basically the closest to the fullest of a shells, just like the P block would be most of the time. Other than in the first period where there's no P block, that's the point. Same with the helium that's in the S block as well, technically. But we put it up there, which is why it probably bothers you that it's over here. But I just do it by block. So that explains that. Lithium. Beryllium. The P block finally appears. Boron. It's actually kind of expensive too. Carbon. Diamonds are also made of carbon, almost pretty much exclusively. It's like a form of carbon, an allotrope, diamond is. But nitrogen after carbon, it's a gas. And this is the majority of air. Nitrogen is. It's like 70% of the air, but 20% here is oxygen, which is essential for respiration. Quite obviously. To most people, but I'm saying most people know that is what I mean. That's what I mean. Obviously, everybody breathes, but not everybody knows that somehow. Excluding like kids, like really young, like toddlers or something that don't know that breathing is required or something. I don't know. I wouldn't be aware of anyone else that wouldn't know that. But fluorine, yeah, 30% fluorine ampule. So that means it's mixed with about like a few 70% helium or something, or argon or whatever the noble gas is in there. And and then it basically makes it to where the fluorine doesn't eat through the fucking glass. Neon, yeah. Yeah, some neon gas in there. So we have a few gases already. There's the neon fluorine gas and oxygen gas, nitrogen gas, hydrogen and helium gas. So there's several forms of gas. There's more, but yeah, sodium. Sodium. It's soft enough to cut with a butter knife, if you didn't know that. I think so is potassium. Actually, most of these are. Early lanthanides too, and most of the S block. But we have magnesium next. Focus, please. Please focus. Magnesium. Little balls. Aluminum, wow. One of the most common metals. Aluminum. We didn't know how to extract this for a while, that's why it was valuable. It was actually valuable at one time. silicon. Silicon, wow. It's a metalloid, like boron. So everything everything after the metalloid is a non-metal. Or after the last metalloid is a non-metal. And everything before the first metalloid is a metal. It's pretty much no exception to that, so. Or actually, there is no exception to that. Full stop, period. That's the way I should have phrased it. Phosphorus. Show me the phosphorus. I think it's violet. Phosphorus, I don't know. I'm not sure. Couldn't be black because that would be too valuable. This was not an expensive set. So I know it's not black phosphorus. But, or it might not be. I don't know. Most likely not. Not black phosphorus. But this is the next one. Sulfur. This is the next element. And it's hydrogen sulfide that smells bad. It's a compound of sulfur and hydrogen that smells bad. But sulfur on its own has no smell. Chlorine. Liquid chlorine. Under pressure. It's usually a gas. So this is really cool. I have a gas ampule in my main collection. Argon. Wow. I know there's not much to see there, but it's crazy that there's argon in there. It's not visible though. But potassium is next. Pretty cool. Look at that. Potassium. Is this leaking? It's kind of slimy. I might just be imagining something. Calcium. Look at that calcium, man. It's a metal. It is. Alright, we finally introduced the D block. Man, scandium is in D. My D block. What in the world, man? Scandium. It's also very expensive, too. Titanium, you know, very well known for strength and lightness and stuff. It's lightweight and strong. But vanadium crystals, this pure vanadium in there, just in crystalline form. That's pretty cool. So vanadium, chromium. Got some chromium. Got some manganese. This is about 4 grams because I added some in there because I have like a 100-gram sample of manganese. There's a bunch of pieces, so I added a bunch of manganese to the manganese. So there's about 4 grams in there. And yeah, it's a lot heavier than the other ones. I like this. Yeah, look at that. Iron. Let's get some iron. See the iron in there? That's what iron looks like, usually. Why is it black? Is that black? Sort of. No, it's just really dark, I think. Well, it could be oxidized. I really doubt that because it looks red or brown, right? Rust, you know? But cobalt is actually it's compared to the rest of these D block ones. Cobalt's not that common. Neither is scandium. Obviously, the precious metals are not. Even mercury is not that common. Rhenium not common either. And then that's about it. But there's the cobalt. I wouldn't say not common, but it's in terms of the price. Cobalt is more expensive, and scandium is way more expensive than a lot of these debug ones, other than the precious metals. Which I do consider rhenium as part of the precious metal group because it's right next to it. It's like, might as well. But, so that would mean, I would explain rhenium's overpricedness too as well. You know, nickel. We'll get to those elements when we get to them. Copper. Let's give it copper. Zinc. Gallium. It's all melted because I guess they did that on purpose. I'd rather have it in liquid form, or in solid form though. Germanium. Pieces of germanium. It's a metalloid, that's why it looks like that. Same with arsenic. Arsenic is a metalloid. It doesn't look like it, but it is. It's got some properties of metals. You'd have to ask a chemist exactly how, but they would tell you, yeah, it's a metalloid. I mean, it's certainly not a non-metal, because that would be weird. That far down into the periodic table in that group. But other than that, yeah, selenium. Yeah, arsenic's a metalloid. Selenium's a non-metal, so it goes to non-metal at that point. Selenium. Bromine. This is one of my favorites. Krypton. Another gas. All the noble gases are gases. That's why they're called that. Rubidium. Wait. Krypton. Yeah. I don't know why I was jinxing myself there. Rubidium. Damn. Rubidium. This stuff's expensive, so I think that's probably like 100 milligrams in there. Or a gram or whatever. Who knows how much they put in there? I don't know. Strontium. You got some of these might be oxidized. Yttrium. Zirconium, which I've heard is a lot like titanium. It's in the same group, so I'm talking chemically and yeah, even structurally, and well, I wouldn't say structurally. Not like in terms of the nucleus, that's not what I'm talking about. I'm talking about, I guess I would just be talking about the chemical reactions, because, well, the physical properties can somewhat be determined by the chemical makeup, right? Physical properties. No, I think they just align. But, what was that one? Zirconium? Yeah. Sorry. Niobium, this is anodized. That's why it's colorful. They just send like an electrical current through it or something in it. Like they do. I think they do the same with the magnetic metals to make them magnets. So, but it has something to do with light. I don't know. I couldn't explain it to you, but niobium, yeah. Molybdenum. Got a lot of little beads of molybdenum in there. Alright, we finally get to technetium, which we don't have because it's not stable. We don't have, I do have it in my main collection, but This is just a display here, so that I put on my shelf. And this is skipping technetium. So we get to the precious metals now. Ruthenium. Very tiny specks of ruthenium in there. You can hear it though. Rhodium, I put a 1 gram pellet in there, and there's some rhodium in there as well. Palladium, little pieces. And I mean little, because listen to that. It's very quiet. Palladium. Silver. So we got all these precious metals and stuff. Rhodium was... Yeah, there's a reason that there's not much in here, because rhodium's a precious metal. I think it's more than $200 in value in this ampule here. Just in rhodium melt value, I think. Actually, for a tenth of an ounce is 450 or something like that. So it'd be like a third of that, roughly. I'm not good at math. Oh, that's 150. Yeah, 150 for that. I already did palladium. What are you doing? Silver, cadmium. Indium. This stuff is cool. You can like put your fingernail indentation in there because of how soft it is. Indium. With 10 stable isotopes, it has the most stable isotopes. That's my thing. I'm the isotope guy. But 10 antimony. Tellurium. Or tellurium, however you want to say it. Iodine. Look at the iodine. That's a solid halogen. That's not common. Actually, there's only one solid halogen. It's iodine. I mean, at standard room temperature is what I mean, obviously, because at some point bromine solidifies if you get cold enough. Same with chlorine and fluorine. It's just probably really cold though. But iodine is solid at room temperature, so. Over here we have xenon, the heaviest noble gas that is stable. Heaviest stable noble gas. Xenon. Cesium. Man, wow. Little ampule in there with cesium in it. It's crazy. Barium. Highly oxidized barium, but looks like barium to me. Lanthanum. Highly oxidized lanthanum. You can see it in there though. The mineral oil doesn't really stop it from being oxidized because the oxygen still gets through, but I guess it slows it down. I'd still like to see what it looks like outside of the mineral oil though. Cerium. 58. We're getting up there, man. And the numbers. 59 protons. 141 nucleons for praseodymium. So that is like... It's just crazy. Like, what the hell? Neodymium. These all react with oxygen. That's why they tarnish very quickly in air. Neodymium. That's why they're in this oil substance. Mineral oil. No promethium. No promethium because it's radioactive. samarium. Yeah. Europium. This is also pretty valuable, kind of like scandium. It's not common, or at least not cheap. Or maybe it's just the vendor I get it from, Luciteria, just charges a lot for it. Who knows? Europium. Gadolinium. Gadolinium. Terbium. Terbium. Dysprosium. Oh yeah, I forgot Atlantinum. That was the start of the F block. I forgot to say that. So that's a new block introduced, which is why we're seeing a lot of this very similar looking metals. In the beginning, they were all like reactive with oxygen, and then after the halfway point there, with gadolinium, see there's, if you ignore lutetium from what is it? Ytterbium, lanthanum to ytterbium, but if you include promethium, then it's 14, but you remove it. So basically, yeah, I got 13 stable examples of an F block. And the first half would be the first 7, and then the second half would be the last 7. And there's a distinct difference between the first 7 being reactive with oxygen and the second half not being reactive with oxygen. I've noticed that very clearly. But dysprosium, you can see how it just looks fine in air. This is in the second half of the lanthanides, not the first half like praseodymium, which is in mineral oil. Holmium. That means somewhere in between the alkaline earth metals and the first of the D block. Or actually, no, sorry. Somewhere in between the first half, somewhere in between the alkaline earths and the first half of the F block. Or the second half, between the second half. So the first part of the second half would be gadolinium. And everything before that, and all the way to the alkali metals, would be all the reactive metals, basically. And then everything over there is pretty reactive, too. Actually, most of the periodic table can react. The only thing that's not reactive over here is the noble gases. But fluorine's reactive, and chlorine and stuff. And bromine. Here's erbium. Just some erbium, thulium. You know, there's a lot of these, aren't there? Yeah, there is. Thulium. Ytterbium. Alright, lutetium's in the D block, technically. People say it's part of the lanthanides that always bothered me. Lutetium. You're probably wondering why. Well, yttrium to cadmium is 10, right? But hafnium to mercury is 9. So obviously lutetium's in the D block. Pretty easy to tell that. But it's always bothered me that they put it down here. It's like stupid. Why? Hafnium. Hafnium. Get that hafnium. Tantalum. Tungsten. Tungsten. Rhenium, or rhenium. Osmium. Oh, here we go. Look how small that is. It's very quiet too, so it's not very much. Iridium, the 1 gram. 1 gram of iridium bead in there that I put in there. There's also some small pieces in there of iridium. It's like the single most expensive precious metal, or rhodium is. Rhodium or iridium, they're both in the same column. And I know the radioisotope reason for why they're so rare is because they only have one stable isotope. Or actually, iridium has two, but they have few stable isotopes. And they're both odd-numbered protons, so they're probably going to have less isotopes to begin with anyway, so. Which is why their abundance is less, significantly. And they're in that group after tungsten or whatever that's also rare from the reason it's rare is because it's only created from neutron capture in stars or in not neutron capture, what's it called, neutron star merger. Yeah, neutron star mergers, but this is platinum. It's only formed during neutron star mergers, which is neutron stars colliding, which is crazy to me. Gold is gold. Well, I don't know if it's only formed there, but that's how it's mostly formed. But gold is gold. Mercury. Mercury. Mercury, you see the mercury. Look at the mercury. Thallium. I got some little, see a little tiny piece of thallium in there, in the ampule. It's not in the ampule because it oxidizes or anything. It's in the ampule because it's very dangerous to humans. You don't want to be touching or consuming that at all. Lead, it's a toxic heavy metal. That's why thallium is in the ampule. Lead is also, so thallium, lead, mercury, thallium, lead, mercury, gold, mercury, thallium, lead. So they're all heavy, toxic heavy metals. And then, but more importantly, lead is the last stable element. So lead's the last stable element, and bismuth has a half-life of 20.1 billion years. So it's not stable. You can't call it stable, and stop calling it stable. Okay, so it's weakly radioactive is what you should call it. Or very weakly radioactive. I mean, the distinction can be made, just how weak the radiation is, but like you could eat it and be fine. That's why it's in Pepto-Bismol. But, or rather, if that wasn't the case, it wouldn't be in Pepto-Bismol, is how I should have said that. But bismuth, this is the last one in this display table, because anything bigger is obviously radioactive, and even bismuth is slightly radioactive as well. So, but yeah, everything bigger is definitely very radioactive, very hard to collect, and therefore very hard to put in this display table. I mean, you could for thorium and uranium. They got somewhat long half-lives, billions of years. That's pretty long, actually. Not too long though, because something like if it's been decaying for millions of years in a rock and an ore, and you get that ore out, the ore is going to be very radioactive. Not from the uranium, but from all the stuff it's been decaying into for the past million years and stuff that's been possibly collecting. Well, some of it might be collecting. It really depends on the decay chain, but yeah, in this video, we're not getting into decay chains because this is just all the stable examples I can think of. So if I wanted to add what's in my collection to this, to show you the big collection, how many more elements it has technetium, which is in the D block, francium and radium from the uranium ore in the S block, promethium in the F block from the uranium ore. I'm also getting a watch hand soon. It's pretty close to delivery. Okay, and then we got up to actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, and einsteinium. All of these in the F block. Those are actinides. That's why they're a different color than the lanthanides there. They're in the 7th period instead of the 6th period F block. That's the 6th period F block. That's the 7th period F block. And then we have, what is this, 3rd? No, wait, 1, 2, 3, 4, 5, 6 for D, and then 2, 3, 4, 5, 6 for P, and then 1, 2, 3, 4, 5, 6, and then 7 for S. And then this would just be, what, 6 and 7 there, yeah. But finally, polonium, acetine, radon. I would have those as well in my collection. In the main one. So when you put all this together, let's see what it looks like when you put all this together. When you put all this together, it's actually quite a bit. And I'm going to do this in standard form because I prefer that as the nuclear guy. I prefer it in the best form possible. That makes the most sense and is, you know, not counterintuitive or anything or anything stupid like that. There we go. That's how it's supposed to be displayed. What's on the bottom there doesn't match on what's on the display table, so I might as well move. Move it, but the display table, or sorry, the collection I have in my, tucked away somewhere in my safe, you know, it contains all of these. The display table only stops here, but you can see it goes significantly further. Over there, let's see, over there. Significantly further to Einsteinium. I can't see on my phone because of the tripod, but the, yeah, I mean, it's crazy how many you can get, how many different elements you can get. I feel like people would be curious about these 4 here. It's just a cube with a bunch of curium in it that beta decays and neutron captures all the way up to here, up to Einsteinium. And the same with the technetium, promethium. There's like uranium ore and stuff. Plutonium, yeah, I have a Soviet smoke detector for that. Yeah. Alright, well, thanks for watching.